discussing the different non-parametric tests that we can use when we violate the assumption of normality in our respective data set. And for this video, we're going to talk about the Wilcoxon-signed rank test. So in the previous video, which I suggest watching if you've not done so thus far, is if we violate the assumption of normality, we can't use our parametric tests that we've learned about throughout the semester. Now, one thing that we can do to potentially alleviate this problem is to transform our data using some type of mathematical function. But in times, we can't reach this normal distribution with some type of transformation, and sometimes it's difficult to interpret what the actual results are if we transform the data too much. And so we can use non-parametric tests when we don't meet this assumption of normality, because these statistical tests, these non-parametric tests, don't require us to follow a normal distribution with our data set. And in part, this is because these tests are assessing medians rather than means. So if we think back to the beginning of the semester, when we talked about the advantages and disadvantages of using different measures of central tendency, means tend to be heavily influenced by outliers much more than our medians. And so when we think about our data being skewed and not normally distributed, it tends to be because of outliers. And so this then kind of goes hand in hand with the use of these non-parametric tests. Now, we shouldn't just immediately turn to these non-parametric tests because they are a bit more limited than our parametric tests, particularly in their statistical power and their ability to actually detect differences. And this tends to lead to higher p-values when we use a non-parametric test, and this in turn leads to a higher likelihood of a type 2 error. So we fail to reject the null hypothesis when in fact it's actually false. And so to alleviate this, in the event that our data is non-normally distributed, we can make sure that our sample size is large enough to alleviate this potential problem. Now, this won't completely eliminate the likelihood of a type 2 error, but hopefully this reduces it to the point where this isn't something that we're worried about when we're making our inferences. Now, in this particular class, we're going to talk about 4 different non-parametric tests, and in this video, we're going to focus on the Wilcoxon-signed rank test. So this test is used to compare 2 paired samples to assess if a population mean ranks are different. So we're going to determine if 2 dependent samples were selected from a population having the same distribution. So some important assumptions that we're going to make for this particular test are that the data are paired and they're coming from the same population, that those data pairs are random and independent, and that the data are on some type of interval or ordinal scale. And we're going to see what this means when we move forward into the example. Now, this test is based on the premise that there's going to be differences in these data pairs, and the larger the difference, the greater their weight is going to be in the test. And one of the keys for this particular test is that if there's no difference between the data pairs, then they're discarded. And this is going to affect our sample size, which will in turn affect our critical value. So let's look at an example to see how this works, because this is pretty abstract at the moment. So let's say that we want to use the Wilcoxon-signed rank test to assess how diet influences body condition of penguins. So we're going to feed these penguins 2 different diets, and we're going to see how this influences their body condition, if they're healthy or not. So we're going to measure the body condition of these penguins when they're fed on sardines for a month, and then we're going to do the same after they're fed on anchovies for a month. And so in this particular example, our null hypothesis is going to be that there's no effect of the diet of these penguins on their body condition. And for our particular sake in this study, we're going to indicate body condition with a number, and the higher the number, the better the body condition of the penguin. So we're at a captive rearing facility, and we select 11 different penguins for this particular study, and we're going to feed them on these 2 different fish species. And so for the first month, we select 6 penguins and feed them sardines, and we select 5 penguins and feed them anchovies. And then we take a month and feed them their normal diet, and then we go to the other diet. And our goal here is to see what the difference is between feeding these penguins sardines versus anchovies. Is one better for them than the other? And so in order to do this, we're going to use the Wilcoxon-signed rank test. And the first step to doing so after we have our data is to calculate the difference between these paired data values. So we simply take the sardine body condition value, subtract the anchovy body condition value, and we get our difference value. Now, one of the keys for this test is that, as we previously mentioned in the earlier slides, is that any individual in which the difference equals 0 needs to be removed from the data set. So this particular individual 5 did not exhibit a difference in its body condition when it was fed sardines versus anchovies, and its difference is 0, so we can then remove this from our consideration and move forward with the analysis. After we have these differences calculated, we're then going to calculate the ranks of these differences. And we're going to rank them based on their proximity to 0. So our first two ranks are going to be for penguin 8 and penguin 10 because their differences are 1 and -1. So these two penguins are tied for the top rank. So rank 1 and rank 2. So we're going to take the average of these ranks, and so they're each ranked 1.5. Now what's important here for this test, in addition to calculating these differences in these ranks, is that we keep track of which of these ranks is positive and which is negative. So here we're going to indicate the negative ranks with a negative sign, because we're going to end up comparing the negative ranks to the positive ranks at the end of this test. So after we've got these first two penguins ranked, we're going to find the penguins that are closest to 0 after these two penguins. So in this case, we find penguin 7 and penguin 9. They both have a difference of -2, which is the next closest number to 0. And so these are tied for the ranks of 3rd and 4th. And so again, we're going to take the average ranks. And for these are both negatively ranked because they both have a negative difference. We're then going to proceed to the next closest number. Penguins 1 and penguins 4 have a difference of 3 and -3, so they're tied for ranks 5 and 6. So again, the average rank and indicating which ranks are positive and negative. We then move to the next closest number. Penguin 11 has a difference of -4, so it's ranked 7. Again, we're keeping track of our ranks here. The previous ranks were the average of 5 and 6, so this next one is 7. And then we move forward and rank the rest of our penguins. Now note here again, we can have ranks that are the same and of the same sign, or we can have ranks that are the same and of different signs. So it's important to keep track of the signs and the values of these ranks. We're then going to take the summation of the positive ranks and then take the summation of the negative ranks. And we're going to use these as our test statistic. And we're going to choose the value that's smaller. So in this particular case, the negative ranks have a summation of 21, and so this is going to be our test statistic, big T. Now we're going to take this test statistic and we're going to compare it to a critical value. So as we've done throughout the semester, we're going to turn to a statistical table, and in this case it's a Wilcoxon-signed rank test table, and we're going to use our sample size and a predefined significance level in which to find that critical value. So our default throughout the semester has been 0.05 significance level, so we're going to continue that. And our sample size in this case is 10. Now we started with 11 penguins, but one of those penguins didn't have a difference between the diets and its body condition, so we excluded it. So our sample size for this particular test is 10. And something very important for this particular test is that our criteria for rejecting the null hypothesis is different than all previous tests to this point. In that in order to reject the null hypothesis, the test statistic has to be less than or equal to this critical value. All the other tests, our test value had to be greater than our critical value, but this is different, and it's a key difference here. Our test statistic for this respective example is 21. And if our critical value is 8, it exceeds this, so it doesn't meet the criteria to reject the null hypothesis. So what we can say here is even though we see some differences among penguins, there's no significant difference based on the diet of the penguins on their body condition using this statistical test. Now, a couple important keys when we're using the Wilcoxon-signed rank test is that we need to calculate the differences of the values of the paired data sets and then rank order the differences. We're not actually ranking the data, we're ranking the differences, and this is going to be key because some of these other non-parametric tests we're actually going to rank the data. So we're ranking the differences, not the actual data. If there's any kind of ties in the rank, we're going to use the mean rank of those ties. And if there's any data pairs that have no difference in their values and the difference is 0, we're going to discard them. And this is going to affect our sample size and in turn affect our critical value. And when we're determining our test statistic, we're going to use the smaller sum of the ranks of the differences. So this is going to be important. And key here is that the null hypothesis is rejected if our test statistic is less than or equal to the critical value, which is different than the other tests that we've conducted thus far. So moving forward, we're going to talk about another non-parametric test in the next video. We're going to talk about the Mann-Whitney U test.